Hey guys, here's the review for Spiral 13. First up we got some trig identities, and what we're trying to do is to verify each identity. In looking at this first one, I'm trying to decide if I want to go for the left side or the right side. They both look pretty complicated. I'm probably going to go with left side just because that tends to be where I start, and if I end up not getting somewhere useful, I'll go somewhere else. Okay. So we've got sine, cosine on the right side. I'm going to start off by converting everything to sine and cosine. So we get sine x over cosine x minus 1 over cosine x over 1 over sine x. That's equal to the same thing as sine x over cosine x minus 1 over cosine x divided by 1 over sine x, which is the same thing as, I'm going to combine these two since they have a common denominator, sine x minus 1 over cosine x, and if I'm dividing, that means I'm multiplying by the reciprocal, times sine x over 1, and that happens to be exactly what we have up here. So I wasn't really sure where I was going, but I ended up getting to a place that worked out for me. For number 2, I've got negative sine x times secant x is equal to tangent x. Well, I'm going to write this as negative sine x times 1 over cosine x, which is very quickly the same as negative sine x over cosine x, which is the same as negative tangent of x, which is what we're trying to get up top. For number 3, we've got sine squared x over cosecant squared x minus 1 is equal to tan x, cotangent x, and then another cosecant squared x on the bottom. Okay, I'm going to look at the left side of this again, and what I'm going to try to do is start by converting everything to sine and cosine and see what ends up happening. So we get sine squared x on top. On the bottom, we end up with, actually, you know what? This looks like one of my other Pythagorean identities. Let me start with sine squared plus cosine squared equals 1. I know if I divide both of these things by, to get cosecant, you need to divide by sine. So sine squared, sine squared, sine squared. So we're looking at 1 plus cotangent squared x is equal to cosecant squared x, which means that cotangent squared x is equal to cosecant squared x minus 1, which is what we have here. So that's the same as cotangent squared x. Okay, I'm going to rewrite that as sine and cosine. So we've got sine squared x over, that's going to be cosine squared x over sine squared x. I'm going to multiply by the reciprocal, so we get sine squared x over 1, and that's multiplied by sine squared x over cosine squared x. Okay, now I'm going to try to start building this thing, which as of right now does not look all that pleasant to build. I know I need a sine over cosine, so I can get that from this. So I can write this as sine squared x over 1 times sine over cosine times sine x over cosine x. All right. I also happen to know that sine squared x over 1 is the same as 1 over cosecant squared x. So now we've got that piece. This is going to end up being tangent of x. So now we've got that piece. And now I need a way to convert this into cotangent. So I'm going to start by writing that as tangent. And what we're going to do is to realize that tangent is the same as 1 over cotangent. And we've got tangent x, and we've got a 1 over cosecant squared x, which is everything that we're trying to get out of that stupid, ugly problem. And we end up with tangent x on top and cosecant squared x times cotangent x on the bottom. I don't know that there's a better way to do that starting on the right side, but there might have been. Lastly, we've got 1 minus secant squared x over secant x is equal to negative sine squared times secant x. I'm going to convert everything to sine first, just to see what happens, or cosine rather, as we get 1 minus cosine squared x, 1 over cosine squared x, sorry about that, divide by 1 over cosine x. I'm going to rewrite this as 1 minus 1 over cosine squared x, and that's going to be times cosine x over 1. I can use some common denominators to rewrite this as cosine squared x over cosine squared x, and that's going to combine to get cosine squared x minus 1 over cosine squared x, and we're multiplying this by cosine x over 1. All right. And then if I take a look at this guy, well, I know that 1 is equal to sine squared plus cosine squared. So I could write that as cosine squared x minus sine squared x plus cosine squared x over cosine squared x. And that's all times cosine x over 1. If I subtract, my cosine squareds cancel out, and I'm left with negative sine squared on top. So we're left with negative sine squared x over cosine squared x times cosine x over 1. One of those guys can cancel out and left with negative sine squared x over cosine x. And I think that's what we're trying for. It's close to what we're trying for, but we're not quite done. So we got to go negative sine squared x times 1 over cosine x, which is negative sine squared x times secant of x. Next up, we got to work with some sum and difference identities. And first thing we got to do is figure out exactly what we're being asked to do. For this one, I happen to notice that if I were to write this as cosine A, cosine B, where A is negative 4v and B is 6v, this could be written as sine A, sine B. That happens to be one of my identities. That's going to be the identity of cosine A minus B. So what I'm going to do is recombine this with my A and B that I figured out. So that's going to be cosine of negative 4v minus 6v, which is cosine of negative 10v. This is a new style of problem in terms of having variable expressions on the inside and having to figure out which one we're dealing with. Okay, similarly for number 2, we get cosine of v. I could write as cosine A. Cosine of negative 2v could be cosine of b minus sine A sine b. Same deal, but now we're dealing with cosine of A plus b. So I'm going to rewrite this as cosine of v plus negative 2v, which is cosine of negative v. Find the exact value of each. First, I've got to start by rewriting these in terms of two angles. I'm just going to try a couple sine things. 13 I know can be written as 4 plus 9 over 12. And let's see if those reduce okay. So that gives us sine of pi over 3. That's nice. and sine of 3 pi over 4. That's nice too. So that's going to look at sine of a and b, where a is pi over 3 and b is 3 pi over 4. So sine pi over 3, cosine 3 pi over 4, plus cosine pi over 3, sine 3 pi over 4. Sine of pi over 3 is root 3 over 2. 3 pi over 4 for cosine is negative root 2 over 2. Cosine of pi over 3 is a half. Sine of 3 pi over 4 is root 2 over 2. That gives us a final answer of negative square root of 6 plus the square root of 2 all over 4. For number 8, we get cosine of negative 7 pi over 12. Okay, I'm going to, again, try to rewrite this as things that I know. So I could do that as cosine of 7 is 3 and 4. So negative 3 pi over 12 plus negative 4 pi over 12. Those reduce nicely, so we get cosine of negative pi over 3. And by that I mean negative pi over 4 plus cosine of negative pi over 3. Okay, so we're looking at cosine of negative pi over 4, cosine of negative pi over 3. Since I'm using plus, that becomes minus. Sine of negative pi over 4, sine of negative pi over 3. And now I'm going to do some evaluation. Cosine of negative pi over 4 is going to be the square root of 2 over 2. Cosine of negative pi over 3 is going to be a half. Minus sine of negative pi over 4 is negative square root of 2 over 2. Sine of negative pi over 3 is going to be the negative square root of 3 over 2. We end up with the square root of 2 over 4, and that's going to be minus negative is positive, square root of 6 over 4. If you want to combine those, you can. Okay, we got to graph a couple exponential graphs, and to do this, I'm going to make a table. I'm going to start my table at whatever makes that exponent equal to 0. So in this case, that's going to be 2. Okay, when I plug 2 in, I get 3 times 1 is 3 plus 1 is 4. So 2 comma 4 is going to be my first point. And I'm going to go for a couple points on either side of this. I'm also going to identify my asymptote. That's a positive 1. But let's go up 1 and down 1 just to see what we get. So we get 3 times 2 to the negative 1 is 3 halves, plus 1 is 2.5. So 1 comma 2.5 would be a point. And then we got 3 times 2 is 6, plus 1 is 7. So we're going to end up at 3, 7. Drawing through there, we end up with something that looks like this. To get credit for this, I need to see 3 clearly identified points and your asymptote. Okay, second one, same deal. We're going to start out with whatever makes that exponent 0. So in other words, negative 1. 2 times 1 is 2, minus 2 is 0. Negative 1, 0 is my first point. I'm going to take this time to show my asymptote as well. Right at the bottom of my graph, I'm going to go down 1 and up 1 from there. 2 times, let's do the negative 2 first. So we get a third to the negative 1 is going to be 6. 6 minus 2 is going to be 4. Negative 2 comma 4 is our point. Next one we're looking at is going to be 1. I'm sorry, 0. So 2 to the 1/3 is going to be 2/3 minus 2 is going to be negative 4/3, or a little bit less than 1. That gives us a pretty good range for us to go through. We know we're going to go towards that asymptote and look something like this. Okay, continuing on, we've got to look at writing some equations for graphs, and these equations are going to be in the form of y is equal to a b to the x plus k. First thing we'll take care of is k, and that's going to be my asymptote. For the first one, it looks like my asymptote is at a height of 1. So we'd write this as y equals ab to the x plus 1. Second thing, I'll look for my y-intercept. That looks like 0, -3 to me. This would be labeled so you can see it much more clearly on your spiral, hopefully. Or you can ask if you can't tell. So we get -3 is equal to ab to the 0 plus 1. b to the 0 is 1. If I subtract 1 to both sides, I get -4 is equal to a. So we've got y equals -4 b to the x plus 1. Now I'm going to look for another point to use, and I see I've got a point 1 comma -7. So -7 is equal to -4 b to the 1 is b plus 1. If I do -1, we get -8 equals -4b. If I divide by -4, I get b is equal to 2. Okay. From here, I have my equation. I've got y is equal to -4 times 2 to the x plus 1. Alright, similarly, we're going to do the same thing for my second guy over here. It looks like my asymptote is at y equals 2. That means we're going to start off with an equation. Y is equal to ab to the x plus 2. Next thing I do is take a look at my y-intercept. 6 is equal to ab to the 0 plus 2. That's going to give us a is equal to 4. Next thing we do is look at another point. I've got a point 1 comma 4, and that's going to give us 4 is equal to 4b to the 1 plus 2. In other words, 2 is equal to 4b. b is a half. And based on this being a decay graph, that makes sense. Putting all together, y is equal to 4 times a half to the x plus 2. Next up, we've got some exponential equations. For these, we need to try to convert everything to the same base. Alright, if I've got 2 and 16, I'm going to convert those both to a base of 2. That one's all set. 16 is going to be 2 to the 4th. And when I put those things together, now I have the same base, so that means that -m is equal to 4. To me, that means m is equal to -4. 14 is going to have a similar level of complexity. Again, these are both base 2 type numbers, so we get 2 to the -2m is equal to 2 to the 2. That means that -2m is equal to 2. Since the bases are the same, the exponents have to be the same. And from that we get m equals -1. For the third of these problems, we've got an 8th, we've got a 4, and we've got a 1. This is actually the tricky part. We'll talk about that in a second. But these other two guys, we can convert into base 2. And that's going to be what we'll take a look at first. 1/8 is going to be 2 to the -3, -3n. On the bottom, 4 can be written as 2 to the 2, 2 minus 2n. And the tricky part is that anything to the 0 is 1. That even means 2 to the 0 is 1. So I could write 1 in any base that I want, which is pretty cool, but we don't always remember that, so I wanted to bring that up here. Okay, I'm going to simplify these a little bit, so we get 2 to the 9n up top. On the bottom, we're going to have 2 to the 4 minus 4n. We still have 2 to the 0 on the right side. Next step, if I'm dividing, that means I'm subtracting these. So we get 2 to the 9n minus 4, and then plus, because minus minus makes a plus. 4n is equal to 0. That gives me an equation that I can use. So this should be 2 to the 0. 9n plus 4n is 13n. Minus 4 is equal to 0. N is equal to 4 over 13. Okay, and finally, we've got stuff in base 3. So I'm going to convert everything to base 3. So that's 3 squared to the negative x plus 3. We've got 3 to the 4th, and on the other side we've got 81 is 3 to the 4th to the 3x. Doing some simplifying, we get 3 to the negative 2x plus 6. We've got 3 to the 4th, and then we've got 3 to the 12x. I'm going to subtract my exponents here. We get 3 to the negative 2x, and 6 minus 4 is 2, is equal to 3 to the 12x. Alright, that means my equation could be negative 2x plus 2 is equal to 12x. That means 2 equals 14x, or x is 2 over 14, or 1/7.